And it's my pleasure to introduce Peter Cameron, who is going to talk about synchronization from automata to weakly perfect graphs.
Well, thank you very much. Can everyone hear me and see my slides? I think it should be okay. Right. Okay, so this is perhaps a little different from what you mostly have, but this is something that I've been thinking about for 15 years now, and I'll explain to you how I got dragged into it, and I'll tell you what some of the recent results are, because it connects with quite a variety of topics, and it's fun to do. Anyway, here we go. So what's an automaton? Well, there are various versions of what an automaton is, but for me, it's a very simple machine. It has a set of internal states, which I'll call omega, and it reads symbols from an alphabet A. And when it reads a symbol in a given time step, it simply changes its state according to some rule. I'll give you an example in a moment. So it reads a symbol and changes its state. And then, of course, it can read another symbol. You might feed it a string of symbols. It reads them one at a time, and after each one, it changes its state. So when it reads a word, each symbol causes a state change. So we get the composition of all the state changes. And what does synchronizing mean? Synchronizing means that there's a word that you can feed into the automaton, so that, which is called a reset word, so that when it reads that word, it ends up in a fixed state. No matter where it starts, you know exactly where it is at the end. So if this machine has broken down and you have to send it to be repaired, before the repairman takes the back off, they want to know that it's in a safe state. So it's important to be able to do something like this. And there are various other applications. Misha Volkov has a beautiful video of an automaton which, in a water bottling plant, makes sure that all the bottles are the right way up, ready to go and be filled. So these are quite useful things. Okay, sorry. Reset word brings the machine into a known state. So here's an example, and you see how I've drawn it. The states are the numbers 1, 2, 3, 4, and the letters in the alphabet are the two colors, blue and red. And I apologize if you can't distinguish blue from red. So let me tell you what they do. Red simply maps around in a cycle, 1, 2, 3, 4, and back to 1. Blue on the outside maps 1 to 2, but everything else stays where it is. So 2 goes to 2, 3 goes to 3, and 4 goes to 4. Now you can check that if you do blue, then if you read blue, then 3 reds, blue, 3 reds, blue, that's a reset word. Let's do an example. Suppose we start from 3. Blue, we stay at 3. 3 reds brings us around to 2. The next blue leaves us at 2. The next 3 reds bring us to 1. And from 1, the last blue brings us to 2. So we end up in state 2. And if you want to, you can check, start anywhere else. You will always end up in state 2. So that's a reset word. And indeed, you can check that it's the shortest possible reset word for this automaton. So given an automaton, how long can the shortest, if it is synchronizing, how long can the shortest reset word be? And the conjecture is that for an n-state automaton, the answer is n-1 squared as the upper bound for the length of a reset word. And this is an old conjecture. It was posed in the 1960s and was still open. And it comes with a health warning. This looks like such an attractive and easy conjecture that you're very tempted to just have a go. But you'll get sucked in very quickly and you'll waste a lot of time on it. And as I say, in more than 50 years, nobody's cracked it yet. So beware. So that's the Cherney conjecture. And I started thinking about this, not because I wanted to solve the Cherney conjecture, but because people I were working with were interested in it and were reformulating it in various ways. So let me tell you a little bit about that. We're going to turn this into semigroup theory. So a transformation monoid is so it's a set of transformations. So omega is a set of states. We have a set of transformations on omega. It should be closed under composition, and it should contain the identity, the map that leaves everything where it is. And now the possible responses of an automaton to reading a word will form a transformation monoid, because, as I said, it's closed under composition. If you read a word and then another word, you just compose the transformations. And if you read the empty word, you stay where you are. So that's the identity. So each letter so the set we're acting on is the set of states of the automaton, and the letters of the alphabet correspond to transitions, and we're allowed to compose them. So we get the monoid or semigroup generated by those transitions, by the given transitions of the monoid. So you can reformulate the Cherney conjecture. It's a question about transformation monoids, and we don't have to mention automata at all. The question would say, suppose you have a transformation monoid on a set of size n, and you're given a set of generators for it, and suppose that you know that there is an element of rank 1, that is, that maps everything down to a single point, then how long is, in the worst case, how long could that element of rank 1 be as a word in your given generators? So it's an algebraic question about transformation monoids. Well, I'm going to give you an entirely different formulation of it in terms of graphs. So the graphs here are just ordinary simple graphs, no loops, no multiple edges, no directed edges, no colors or weights on the edges. So unlike that picture of an automaton that I gave you, which was a directed graph with colors on the edges, these are just ordinary simple graphs with no colors. So that's a graph. And if you have a graph, it might have some endomorphisms. An endomorphism is a map from the vertex set of the graph itself, which carries edges to edges. I don't care what it does to non-edges. If you take a non-edge, it might map to a non-edge, or it might map to an edge, or it might collapse to a single vertex. But edges go to edges. And so in particular, you see, because there are no loops, edges can't collapse to single vertices. So, and also, if you look at all of the endomorphisms of a given graph, that's closed under composition. It contains the identity, and so that is a transformation monoid. So here's another source of transformation monoids, endomorphisms of graphs. What's the connection between them? Here's a first hint that there is a connection. As long as your graph has at least one edge, its endomorphism monoid is not synchronizing, because remember, synchronizing means you can collapse everything down to a single point. If there's one edge and you're restricted to using endomorphisms, you can't collapse that edge. It must remain as an edge wherever it maps to, and so there's no reset word. So the endomorphisms of a graph with at least one edge do not form a synchronizing monoid. Well, it turns out that's the unique obstruction to synchronization. And let me explain that, and also explain the weakly perfect graphs in the title. So the clique number of a graph is the number of vertices in the largest complete subgraph. And the chromatic number is the smallest number of colors that you need to color the vertices so that adjacent vertices get different colors. So these are familiar things in graph theory, but the clique number cannot be bigger than the chromatic number. Oh, I've misspelled chromatic, sorry. Clique number can't be bigger than the chromatic number, because if you have a complete subgraph of size m, let's say, you're going to need at least m colors to color it so that the ends of an edge get different colors. So the chromatic number is at least as big as the clique number. If they're equal, the graph is called weakly perfect. I'm not terribly fond of that name. It's derived from things called perfect graphs, where this condition holds not just for the graph itself, but for all of its induced subgraphs. But weakly perfect simply means clique number equal to chromatic number. And so if a graph is weakly perfect, then it has an endomorphism, a proper endomorphism. Because if you take a coloring of the graph, so let's suppose that M is the common size of the clique and the coloring. So you've got a coloring with M colors. You identify the M colors with the M vertices in your clique, and then you map any vertex of a given color to the corresponding vertex in the clique. And because edges get different colors, an edge will go to different vertices in the clique, so it really is an endomorphism. So weakly perfect graphs have endomorphisms. And here's the connection with synchronization. Let's say that a graph is trivial if it's either the complete graph with all possible edges or the null graph with no edges at all. These are not terribly interesting graphs, but we need to have this definition so that we can state our theorem. So you have a transformation monoid. It's non-synchronizing if and only if it's contained in the endomorphism monoid of some graph. Well, if it's one way round, I've already explained this. If it's contained in the endomorphism monoid of a graph with at least one edge, you can't collapse that edge, so the monoid can't be synchronizing. The other way round is the more interesting part, and the graph that you use, you can assume that it's weakly perfect. You can, in other words, to prove this theorem the hard way, you have to take your transformation monoid, which is given to be non-synchronizing, construct from it a graph, prove that it's weakly perfect and that M is contained in its endomorphism monoid. So I will sketch the proof because this is about the only thing that I'm going to prove. Endomorphisms can't collapse edges. So as I said, the endomorphism monoid must be non-synchronizing. The other way around, suppose we have a transformation monoid and we have to build a graph from it. So how do we build the graph? I've got to tell you what the rule is for joining two elements of omega by an edge. And the rule goes like this. I'll join S and T if and only if there's no element of the monoid that maps them to the same place. In other words, you can't map S and T to the same vertex by any element of the monoid. So that'll define a graph. And that's going to be the graph that will do the business for us. So what do we have to show about it? We have to show that it's non-trivial if and only if M is non-synchronizing. In other words, if you can't collapse everything to a single vertex, there are two vertices that you can't collapse together. And really that's because if you could collapse any two vertices, then you just do that over and over again, and everything will get collapsed to a single vertex. Second thing, M is contained in the endomorphism monoid of this graph that we've just built. So you have to take an element of M and show that it maps edges to edges. And that's not so hard, you just do it. And finally, you have to show that this graph that we've built is weakly perfect. It has clique number equal to chromatic number. So that's what's needed to prove the theorem. So let me just give you a very quick sketch of the second point. Suppose that M is not contained in the endomorphism monoid. So there's some element of M that's not an endomorphism of the graph. So it must map an edge either to a single vertex or to a non-edge. Well, if it maps ST to a single vertex, then we shouldn't have joined S to T because the joining rule is we join them if and only if no element maps them to the same place. So they shouldn't be mapped to the same vertex. Now let's suppose that they get mapped to a non-edge. A non-edge, by definition, is some element of the monoid that maps the two ends of a non-edge to the same place. Let's call it M primed. So if SM and TM were not joined, then when you apply M primed, they would go to the same place. But it's a monoid, it's closed under composition. So M composed with M primed is an element of the monoid that maps S and T to the same place. And that's it. To show that clique number is equal to the chromatic number, basically you take an element of minimal rank, show that that's a mapping on the whole vertex set down to a smaller set, show that that's coloring, different elements go to different elements get different colors, So they go to different places under this mapping, and its image is a clique, and then you have a clique and a coloring of the same size. So what's the good of that? Deciding whether an automaton is synchronizing, I didn't mention this earlier on, but there's a polynomial time algorithm that will take an automaton and decide whether or not it's synchronizing. So it's easy to decide whether an automaton is synchronizing. It may be more difficult to decide what the shortest synchronizing word is, but we can decide whether it's synchronizing. We seem to have replaced this by a much harder problem, because we have to build a graph, check that its clique number is equal to its chromatic number, and both of those things are NP hard to compute. So this is not necessarily a step forward, but the point is that the easy problem only refers to a single automaton, whereas once we've got this theorem, we can say whole classes of automata are synchronizing or non-synchronizing, because we can build these graphs and show that the automata we've built are endomorphisms of them. So it is of some value. But if you go back to our introductory example, one of the basic transitions was a permutation. Remember, the red just cycled the 4 points round in a cycle of length 4. That's a permutation. And the other was not a permutation. So I'm going to now talk a little bit about automata with the property that all but one of their transitions are permutations. And I think my colleagues who are working on this problem were hoping to settle the Cherney conjecture for this special class of automata. And that's a reasonable thing to do, because it's known if none of the transitions are permutations, the conjecture is true. So we can assume that at least one is. So all but one, and then try and say all but two, try and work on from there. It hasn't come, they haven't managed to succeed with that, but that was the thought behind this. So let me tell you a little bit about permutation groups. This may be familiar to some, but I'll give you what may be a slightly different take on the basics of permutation group theory. It's the oldest part of group theory, going back at least to Galois, probably to Lagrange if you really want to. But so a permutation group, from what I've said so far, I can define it to be a transformation monoid in which every element, every mapping is a bijection. So a transformation monoid where all the mappings are bijections. And because I'm only dealing with finite sets, if you take, right, I'll start from the top of this slide. We're going to define basic properties of permutation groups by a more or less set way. So I have a set omega, and I'm going to talk about various kinds of structures on omega, which could be graphs or something else. And I'll call such a structure trivial if it's invariant under the whole symmetric group, right? So if every permutation leaves this structure invariant. And my definitions will be of this form. A subgroup, a permutation group, which is a subgroup of the symmetric group, has a certain property, say P, if it preserves no non-trivial structure of a certain type, X. So that's going to be the format of my definition. So here we go. A permutation group on omega is transitive if it preserves no non-trivial subset of omega. So the trivial subsets, the ones that are invariant under the whole symmetric group, are simply the whole of omega and the empty set, right? The usual definition would say G is transitive if whenever you take 2 points of omega, you can find an element of the group carrying one to the other. Well, just to prove one way around that this is the usual definition, suppose there was a non-trivial subset fixed by omega. So it's non-empty and it's not the whole of omega. So you can take a point in your set and another point not in your set, and the usual definition would require you to carry the first to the second, but that wouldn't leave the set invariant. So that's essentially why this works. So transitive means preserves no non-trivial subset. Primitive, which is something that's very important in permutation group theory, says transitive and it preserves no non-trivial partition of omega. So the trivial partitions, the ones that are invariant under the whole symmetric group, are the partition into single parts of size 1, and the partition with just one part, with everything in the same part. Any other part is non-trivial, and if no non-trivial partition is fixed by G, then we call G primitive. The point is that if G does preserve a non-trivial partition, we can break it down into smaller groups. There's a group permuting the parts of the partition and the group fixing one part acting on the points of that part. And we can build, to some extent, reconstruct the group from that. So primitive is a nice condition to have. And a permutation group is too homogeneous, or some people say too set transitive, if it preserves no non-trivial graph on omega, where the trivial graphs are the complete null graph like before. Because too homogeneous means you can carry any set of size 2 to any other. Well, if there was a graph preserved, if one of those sets was an edge, the other would be as well, and you'd have the complete graph. So either you have no edges or you have the complete graph. So that's the condition here. So I'm going to add another one. I'll say that a permutation group G on omega is synchronizing if it preserves no non-trivial weakly perfect graph on omega. Weakly perfect, as I defined before, it means that the clique number is equal to the chromatic number. Now, what's that got to do with synchronization, as I've been talking about it? So I have a bit of explanation to do. The point is that if you have a permutation group, you can think of it as a transformation monoid, but it can't be synchronizing unless the domain has just one point, because all its elements are permutations. They're all bijections. There will never be anything that collapses you down onto a single point. So we're going to hijack the word synchronizing, and we're going to use it in the sense on the previous slide, but we need to explain what we're doing, and this is the theorem that explains it. Permutation group G on omega is synchronizing if and only if for every non-permutation F, that if you take the monoid generated by G together with F, that should be synchronizing. So that's the first step in answering this question that I mentioned before. If you have a group with the property that whatever non-permutation you add to it, you get a synchronizing monoid, then I will call the group synchronizing. So that's the name for this class of groups. So if you look at those statements on the previous slide, you can see that synchronizing lies somewhere between primitive and too homogeneous. Too homogeneous, that means it doesn't preserve any non-trivial graph. Primitive means it preserves no non-trivial partition. You could represent the partition by disjoint union of complete graphs on the parts. That's weakly perfect, and that would be preserved if the partition is preserved. So this is stronger than primitive, weaker than too homogeneous. And a quick sketch of the proof. If G preserves a non-trivial graph with clique number equal to chromatic number, as I pointed out, this graph has an endomorphism, which is not an automorphism. It collapses everything down to the clique. And so the monoid generated by G and F preserves this graph, and so is non-synchronizing. And conversely, if this monoid preserves a graph, then G is certainly a group of automorphisms of the graph. And by the way we did the construction, we can say that the graph is weakly perfect. So now, the problem that they got me involved with was, now I can state, which permutation groups are synchronizing. So can we describe in some sense all of the synchronizing permutation groups? So we don't know the answer to that yet, but just a couple of years ago, we made a big step forward, and I want to tell you about that. So a synchronizing group is transitive. For if G preserves a non-trivial subset, you can take the complete graph on that subset with all the other vertices isolated. That's a weakly perfect G invariant graph, and it's non-trivial. Synchronizing group is primitive. I more or less explained this before. You take the disjoint, if there's an invariant partition, you take the disjoint union of complete graphs on the parts of that partition. And So once we're into primitive groups, we're into very familiar territory for permutation group theorists. So there's a theorem called the O'Nan-Scott Theorem with a very interesting history. It was proved completely independently by Michael O'Nan and Leonard Scott. They both talked about it at a conference in Santa Cruz in 1979. And there was a preliminary version. I wasn't at the conference, but there was a preliminary version of the proceedings. Terry Gagan, who'd been at the conference, let me borrow it, and I read these papers. But when the final version of the proceedings came out, O'Nan's paper had disappeared, only Scott's remained. And why were they doing this in 1979? Well, it turns out that at that point, it was only a couple of years in the future that Daniel Gorenstein would announce that the classification of finite simple groups was essentially finished by tidying up a few loose ends. Well, tidying up the loose ends took 25 years, but that's what Gorenstein said then. And of course, then people start thinking, oh, well, it's all done, nothing more to do. But anyway, it turns out, though, that a good part of the O'Nan-Scott theorem was already in Camille Jordan's Traité des Substitutions published in 1870, if I remember correctly. So all that I'm going to need is in there. And basically, it classifies finite primitive permutation groups into 4 types. First of all, wreath products with the product action, then affine groups, then groups of simple diagonal type, and then almost simple groups. On the next slide, I'll tell you about the first, second, and fourth of these categories. I won't linger on them, but the third is the one where there's been an important breakthrough that I wanted to say a little bit about. So the easiest way to define wreath product type is to say they're the automorphism groups of Hamming graphs. So what's a Hamming graph? You take all words of fixed length over a fixed alphabet, and you join 2 vertices, 2 words, if they differ in precisely one coordinate, if they agree in all the other coordinates. And of course, Hamming was a coding theorist. And if you're sending a message, a word, through a noisy channel, and you assume that it's possible that one letter of the word will be changed during transmission, but if you can assume that it's very unlikely that more than one will be changed, well, you want to know exactly what a word could be changed to, and that's what adjacency in the Hamming graph tells you. So Hamming graphs are weakly perfect. I'll leave that as an exercise. But anyway, these groups all preserve Hamming graphs, so they're non-synchronizing. Affine groups, you start off with a vector space over a prime field, a field of prime number of elements, and the elements of the group are, you apply a linear transformation to the vector and then add on a constant vector to the result. And so it depends what linear transformations you allow yourself. You take you add on all possible constant vectors, but what linear transformations do you use? Well, sometimes you get a synchronizing group and sometimes you don't. And the answer to that is not completely known yet, though there is some work on it. And finally, the almost simple type are the type that lie between a simple group and its automorphism group. And it follows from the classification of finite simple groups that the gap, the quotient of the automorphism group of T over T is very small compared to T. So this ties the group down fairly precisely. But unlike the other 2 cases, we don't specify what the action as a permutation group is. That describes it as an abstract group, but not as a permutation group, so it's arbitrary. So the same group might be synchronizing in one action and non-synchronizing in another, and indeed both synchronizing and non-synchronizing groups occur. So that is still a bit mysterious, but I want to talk about diagonal groups because this is recent work with Rosemary Bailey, Cheryl Prager, and Chava Schneider. And in fact, this was one of the few not entirely bad things caused by the pandemic. We were at a meeting in Cambridge at the Isaac Newton Institute when the pandemic struck and things were locked down they sent us all home. So Rosemary and I were able to sit on the sofa together and prove a theorem. And the theorem we proved, I think, is a beautiful characterization of the geometries that are preserved by these diagonal groups. But so I'm going the wrong way. They are permutation groups. They act on a set of size order of g to the m. And the ones in the O'Nan-Scott theorem, you take G to be a non-abelian simple group. But in our formulation, G can be any group whatsoever. So you can start with any group G, any integer m greater than 1, and you can build a diagonal group. So I'll just say briefly what you do. For some reason, I've changed from G to T on this slide. T is the group now. There's a graph here. The graph we call the diagonal graph. It's a Cayley graph for the group T to the m. And so that means the elements of the group are the vertices are the elements of T to the m. And you join two of them if you get from one to the other by multiplying on the left by an element of this union. So we have m plus 1 of these sets. M of them are just what you get by fixing all the coordinates except 1 and letting that coordinate take all possible values. And this looks like what I just told you about the Hamming graph. In fact, if I stopped there, I would have given you a definition of the Hamming graph. But there's more to it. We put in also S0, which is the diagonal of the direct product. So it's the set of tuples with all components equal. So the joining rule is we join two elements of T to the m if either they agree in all coordinates except 1, which is the Hamming graph, or you can get from one to the other by multiplying on the left by a constant vector. And this S0 seems to be rather special and different from S1 to Sm, but in fact there's complete symmetry between them. You can permute them arbitrarily by automorphisms of the graph. So there's complete symmetry between those. Now, two cases, these are familiar graphs that have been looked at before. If m is equal to 2, basically you take the Cayley table of the group T, that's a Latin square, and from any Latin square you can build a strongly regular graph. The vertices are the cells. You join two vertices if they're in the same row, same column, or they have the same entry, and that's the Latin square graph of a Cayley table. When the size of the group is 2, this is the folded cube. So you take the m plus 1 dimensional cube, you identify antipodal vertices, and you get 2 to the n vertices, and that's called the folded cube. And in general, this class of graphs, these diagonal graphs, we think potentially interesting to at least to algebraic graph theorists and possibly more widely, especially because of their connection with Latin squares. So why are they non-synchronizing? Well, the whole page conjecture, I'm sorry, I'm running over slightly over time. I've very nearly finished. This is the last slide, essentially. The whole page conjecture, which was proved in 2009, shows that the diagonal graph over a finite simple group has clique number equal to chromatic number. And so that shows you that permutation groups of primitive groups of diagonal type, dimension at least 2, are non-synchronized. And indeed, all of these diagonal graphs are weakly perfect, except if m and the order of t are both even and the CL of two subgroups of t are cyclic. But I won't say any more about that case. Here are the references. That's the end of my talk. So thank you very much, and sorry for running over a bit.